I think it is hard carbide. Okay. So, yeah. Okay, any question?
Good. It's just what I wanted.
Okay. Do you like the spectrometer?
Here's the laser. You got the laser. And hey, just hand it to me when you're done. It's my turn.
Group 5, please.
One moment.
It should be all set.
Photoelasticity.
Yes. Alright, well, I'm going to get started. So, for our mini project for Physical Optics Lab, we studied photoelasticity. Just essentially put, photoelasticity is the results of stress-induced birefringence, and this is really useful in studying mechanical systems. So essentially, the gist of it works, I'm just going to preface this so that you have this in mind while I'm presenting, is that you have polarized light that either is going to be transmitted or reflected off a stress-induced birefringent material. And as a result, you're going to see fringes, but these aren't fringes that are associated with interference. They're fringes from the fact of the polarized light traversing different thicknesses as a result of this stress that's acting on this object. So this is more akin to wave plates rather than is interference. So I just want to get that out of the way so that there wasn't any confusion. But as I was saying, this can be used to study mechanical systems, either in transmission or reflection. I have an example. I have an example down here of an interesting study done in sports physiology department over in Britain, which is somewhere in England. Not Britain, like Britton. Anyways, essentially, the blunt of their project was they're interested in studying the impact of a runner's gait at the bottom of their stride. So what they did was they would have a runner at full tilt speed step on a plastic material, and as a result of the runner stepping on plastic material, they would induce birefringence in the material, and they were able to measure the stress pattern of that gait as a result, and they were able to study how how different types of gaits can affect impact. Anyways, moving on. So overview of what this talk is going to cover. So I'm going to go through the theory behind birefringence, which is at the root of anisotropic materials, and we're going to be looking at crystalline structures at first to get an idea of how this that theory can relate to photoelasticity. From there, I'm going to talk about how you can use a polariscope to study anisotropic materials and relate that to stress-based measurements. Finally, we're actually going to talk about two different types of experiments that we did. The first experiment was determining the plane of principal stress in material, which we measured with a ruler. And the second experiment was determining planes of shear stress in the material, which was done in both a protractor and a plate, which were all plastic materials. Yeah, keep moving on.
Can we do it with aluminum?
If you coated it with a plastic material. Like I was saying in the beginning, you can run these types of experiments in reflection as well. But we did purely transmission polaroscopy in this study. Anyways, so what is anisotropy? Anisotropic materials. So this is characterized by the dielectric tensor of the material. So essentially what it means for an object to be isotropic is that when polarized light propagates through it, it's invariant of direction. Well, anisotropic is the opposite case of that, where the direction of polarized light heading into material does matter. There are three cases that are of interest. First, I already mentioned, which is isotropic. The second case is when these two dielectric components are equal, but this Ez is not. And this is denoted as uniaxial. And then perhaps maybe the more common case is when none of these diagonals are equal, and as a result, you have a biaxially anisotropic material. So what does the dielectric tensor do to the light that's propagating in it? Well, essentially, it retards the phase front of the material and slows down the light that's propagating through it. So polarized light is consisting of perpendicular and a parallel component known as the S&P polarization states of the light. So essentially what happens when you have light that runs through an anisotropic material, it will retard one polarization state and the other will travel at the same speed. And as a result, when light propagates through, a new polarization state is made. What I have up here is the map for the uniaxial case. One other note that I should make is that the state of light that experiences the normal traverse from the non-birefringent component is known as the ordinary axis, and the one that's retarded is known as the extraordinary axis. Up here, I borrowed a piece of calcite from Dr. Kapur. This is a geometrical effect that's seen from anisotropy of the material, known as double refraction. Moving on. So some common anisotropic devices include quarter wave plates and half wave plates, which will change the polarization state of light that propagates through it. Here I have two linear state polarizations, and in the quarter wave plate example, light that propagates through it will become circular polarized, whereas in a half wave plate scenario, the linear polarized light is just shifted by 180 degrees. The more interesting anisotropic device is the liquid crystal display, which can be programmed to have non-locally birefringent zones, so you can actually like control the wavefront of light that goes through it, not just with one whole plane, but with like multiple individual planes, so you can like engineer the wavefront. But the component of birefringence that we're interested in here is that due to stress induction, and this is known as the photoelastic effect. So essentially, this comes about when an object is stressed. The quote-unquote crystalline structure of the material is deformed, and as a result, the dielectric tensor changes. And for the purpose of our experiment, we say that this relationship is roughly linear. But we have a couple examples of birefringence induced in plastics shown over here. Common silverware and protractors are pretty illuminating examples. So maybe the last real theoretical piece that should be emphasized is that I brought up the uniaxial case, but in order to do our experiment, we considered our materials to be biaxially stressed, meaning that none of the dielectric diagonals are equal. And this is where that component of the stress being linear proportional to the phase retardation actually works out. So essentially, when you have, think of a cube of material, the approximation that we're making is that the stress in this direction and the stress in this direction are constant. And then in our material, we're also looking at really thin materials. So as a result, the stress in that direction is approximately 0. So from this, we were able to find that the phase retardation is actually just linearly dependent on the shear stress, which is the difference between those two stress parameters in those two different planes. And this constant coefficient material here, known as the stress optic coefficient. Keep moving. So these are the stress patterns that you're able to view with these photoelastic materials. There are two types of patterns. The first one is the isochromats, which is shown by these rainbow colored patterns down here. These isochromat patterns are formed on planes where the shear stress is of constant value. And this is related optically because along these shear stress planes, this is also the plane of constant phase delay. So you notice that we have these rainbow patterns. The reason why there's separate wavelengths on each of these patterns is due to this constant phase delay for each wavelength. So instead of thinking this as like a uniform crystal, really what you should be thinking about is each section of the plastic is its own segment of a crystal, so that it has this continuous property of phase retardation throughout the material. The other aspect pattern that we're looking at here are called isoclinics. Isoclinics are the point of where stress is applied, and as a result is the principal stress axes in the material. The reason why these isoclinics appear black, because at these components of the material, the phase retardation is 0. So all wavelengths are passed as a result. Over here, I have a diagram of the stress trajectories of what's going on in the material. And essentially, what you should get out of this diagram is that depending on where isoclinic occurs in your material, the stress trajectory in that material is normal to isoclinic. So if you try to imagine this picture overlaps here, then the stress trajectory along the isoclinic is actually along this way. So how do you study these things? So I've been showing you some images of an object that is exemplifying this photoelastic effect. But in order to actually view it, you actually need to put it in something called a polariscope. So what a polariscope consists of is an unpolarized light source in a set of linear polarizers. The first one denoted as linear polarizer, and the second one denoted as cross-analyzer. So unpolarized light will go through a first polarizer and become linearly polarized, and then it'll pass through the material, and as the general result, the light will become elliptically polarized. And then finally, we can look at the output, those birefringent patterns that I was showing you earlier, by the cross-analyzer, which actually ends up controlling the intensity of the output. So the isochromats can be seen at any angle because, in general, the light that's emitted from the isochromats is elliptically polarized. So, a component of that will pass. But that from the isoclinic, since it has 0 phase retardation, will remain linearly polarized after it passes through that. So that's physically why you can see those dark spots in the polariscope, because if this linearly polarized light goes through this and isn't retarded, this cross-analyzer will be at 90 degrees past axis there, and as a result, all the light is blocked. This is a diagram of our setup. So essentially, we approximated a white Lambertian source, and all a Lambertian source is it's a source that's irradiance is invariant of the angle relative to the normal of the surface. And as I was saying earlier, we use light so that we can see those isochromats and define those isoclinics. So we have this white Lambertian source, and then it runs through the polarizer. So this is stacked instead of laid out. And then a birefringent sample is placed in between the linear polarizer and the cross-analyzer, and we image it with a USB camera that Mark will show you here in a little bit. Go ahead. So the setup that we have here isn't exactly what we did with the experiment. So the light source over over there is kind of like a light mat, but we actually made our measurements. What type of light source is this again?
It's just an incandescent halogen bulb.
Okay.
It's like a white, light.
So the reason why we used the incandescent bulb is because the spectrum of it is more continuous than that. And we saw that in some of our measurements, and it messed up some of our measurements. So essentially, we took this incandescent bulb, and then there was a diffuser, which was a sheet of paper directly underneath it, and then a linear polarizer, and then the sample would be placed there, and then the camera was set on top right here. Our camera's physical over here, but here's a picture of it. It's just a general USB cam. Nothing special, nothing high resolution.
It's 1080.
Anyways, Mark will take over from here in explaining the actual measurements.
Okay. So essentially, the first experiment that we conducted was to determine, as Luke said, the predominant direction of stress, as I would call it, inside our material. And so the way that we went about doing this was to essentially take advantage of this property that when our material, well, let me just pull up the equation here. So when you analyze when you look at the geometry of the polariscope and kind of analyze the intensity that's passing through it, you'll see that for any given dA of our segment infinitesimal area of a birefringent or a photoelastic object, you will pass this intensity as a function of the angle of the one principal stress axis at that point to the polarizer, and as a function of this alpha, which is the phase that's inducing. So notice that this equation, it looks maybe like superficially similar to Mollis's law, right? Which was the cosine squared theta that you get when you have two linear polarizers. So this is maybe something that we expect because we have two linear polarizers.
You started with 90 degree, so cosine 90 minus gives a sine square. Cosine square.
Right, but
No,
there's
I'm
more to this because there's also component phase retardation.
I'm not. Yeah, it may just be.
So
a
it's not just
maybe
Moll's law. It's something on top of that.
No, I am
Right.
talking about the first
the
sine
sine
square.
versus cosine.
I mean,
So it's-
yeah,
it's-
I agree.
It is
But
cosine square 90
With 90.
minus 6.
Right. So it's just this phase changed cosine, and I think that maybe just comes because we're measuring our theta with respect to the y-axis rather than the x-axis. But this second term, the sine squared of alpha over 2, this alpha, like I said, is the phase introduced by our infinitesimal area. So, or the phase between the two like polarizations, right? So you'll notice that anytime that this is a multiple of n pi over 2, so a full wave, this will actually go to 0, which tells us that in the event that we have at any given point in our object, if it's acting as what I would call a full wave plate, which is to say that the light that comes out from that point is in the same polarization state as it entered, then we will return no intensity because it'll be blocked by the analyzer because it's coming in normally polarized to that analyzer. So we basically take advantage of this property right here, this intensity profile to determine the direction, because our object, when the predominant direction of surface is in line with our polarizer or analyzer, will return no intensity, right? Because of this theta right here. So that's kind of illustrated in this diagram, where you'll see that for this, where the birefringent material, the predominant direction of stress is in line with our input polarization, then we get a dark spot. When it's normal, we also get a dark spot because in this case, the light will be traveling along the direction of the second principal stress axis, which is, again, will not induce any phase because it's a single index along that axis. And so we'll again return no light. But in the event that it's at some angle to our polarizer and cross analyzer, then we'll get light out. So we use a program called ImageJ to do this. So essentially, we put a ruler into our field of view here, underneath our camera, and had this kind of makeshift angle measurement system that you can't quite see around the edge, but we have kind of angle demarcations around here. And we essentially took full field intensity measurements of our ruler, of our polariscope plane, including the ruler, for angles of a ruler at 10 degrees increments through a whole 90 degrees. So you can see that our ruler as oriented right now is at what we would call 0 degrees. And you'll see that there are dark fringes through the center here, which suggested to us that through this center of our ruler, we have a stress that is in the collinear with our analyzer or our polarizer, right? So because if our stress is in either the vertical or horizontal direction, which correspond to the analyzer and polarizer directions, we will be the input light will be essentially having no induced birefringence because it's in line with our stress direction. So
Can you show us something now?
we will. No, I'll have a whole demonstration at the end. I just want to get through our
Okay.
experiments. Don't worry. We'll get there.
Because most of these pictures are available everywhere.
Yeah. But we actually did like some like measurements here. So we did some calculations. So you can see here's 0 degrees, 45 degrees, 90 degrees. You'll see at 90 degrees and 0 degrees, they're effectively the same with this dark fringe in the center, which it gets to that 90 degree periodicity that I mentioned. At 45 degrees, however, well, 40 degrees, we actually see some intensity in the center. And we also took these just kind of reiterate what I've been saying, that we get this dark fringe in the center. These are intensity profiles we took. So you can see dark fringe in the center, and for 40 degrees, we have a bright fringe in the center. This is the data we took that corresponds to our 10-degree increments, the intensity, relative intensity of our full field of view of the polariscope. And so the dots correspond to the data we took, just using what I would call like the image intensity. This isn't like a real intensity taken with an intensity meter. It's kind of just like the average gray value of the image, which we did just using ImageJ. So it's kind of a pseudo intensity measurement, but it gets at the kind of relative intensity of these images as we go through the 90-degree rotation. This blue line I fit to it is a model that we determined based on the previous intensity measure or intensity kind of model that I showed earlier. So that was the intensity that I showed you earlier was for any given infinitesimal area segment, and it included that alpha term. So we basically decided that as we rotated through since we have a bulk material, like many infinitesimal area segments, as we rotate through that phase term will essentially be averaged out across this, because the phase will essentially be randomly oriented through the material. So we kind of just took that to be some constant factor and lumped it in with our I-naughts. And we also, because that one was only considering the angle with respect to the analyzer, so it had a 180 degrees periodicity, we also doubled the angle in our sine squared, which gave us the 90-degree periodicity we were expecting. And I introduced this delta, this phase factor, that allows us to kind of account for basically where the center of our curve should be, where the center of our intensity profile should be, because assuming we're not starting in line with anything. And so doing this, we can see we actually had a pretty good fit with our model. And it had a maximum value at 42.66 degrees, which means that when our ruler was oriented at 42 degrees inside our polariscope, we had a maximum intensity coming through. Which, if you remember that the predominant direction of stress corresponds to the minimum intensity, it tells us that if we just add 90 degrees to this, or subtract 90 degrees, we'll get to, or I should say 45 degrees. Yeah, 45 degrees. We'll get back to our, what would be kind of the effective, like, angle of our predominant direction stress. So all this is to say that our ruler had what would be a roughly 2-degree direction of stress along its one of its axes. I want to say it's kind of ambiguous whether it's along the long axis or the short axis of the ruler, because there is that 90-degree periodicity. It's whether it's in line with the analyzer polarizer. But based on images that we'd seen in textbooks, the fringe pattern that we got out of our ruler seems to correspond to a stress that's along the width, the short width of the ruler. So not this direction, but in this direction. So that was the first experiment. We also did a radially stressed object. So this is not linearly stressed, but radially stressed. And we expect, because like a radial stress profile would essentially mean that the the trajectories would be kind of going out to our edge, right? Which means that, and you can see that the isoclinics here, which correspond to the directions of our stress, correspond to the regions where the stress is aligned with our analyzer polarizer. And our analyzer and polarizer are oriented horizontally and vertically. So these regions you can see are in line with the direction of our stress. So just looking at the image, you can tell that the stress is going from along this direction. And as we rotate it, you see that the pattern doesn't change, which is what you expect from a radially symmetric distribution. And here's more stress profiles, just essentially reiterating that like the isoclinic has no intensity, and along the off isoclinic we have some fringes. Okay, so that was the first experiment. So that was kind of like something we just thought would be, when we kind of started doing this experiment, we decided would be maybe a interesting kind of quantitative thing we could get at, because this is a very qualitative experiment by and large, but we wanted to have some quantitative values to kind of put on the page. So that was the first idea we came up with. This second experiment was maybe a little bit more ambitious, and we decided, okay, we don't want to say where the direction of the stress. We want to actually say what the value of the stress in the object is. So we essentially wanted to find some way to get this sigma 1 minus sigma 2 term, to isolate that. And in order to do that, we need to essentially know the C value, which is dependent on the material that we're using. And because most of the objects we have are of some unknown construction, we don't really know what the material is, it's difficult to know what the C value is. But we were able to obtain a source that gave like values for this stress optic coefficient for a variety of plastics, which, you know, everything that we've looked at so far is plastic. So this those values we decided could be used in order to determine this stress sigma 1 minus sigma 2 value.
Shear stress.
Shear stress, yes. So the number that we arrived at, or that we utilized for our measurements, was actually, it was the value for polycarbonates, mostly because we were able to find just a pure polycarbonate sheet that we used, that we will show you in just a few minutes here. So we did this through a couple methods. So the first method was what I call a pseudo-monochromatic method, which is to say that instead of looking at the actual color fringes, we can maybe just look at some so it's difficult to see this, but these are the red, green, and blue channels of our images. So we
intensity and distribution at different wavelengths.
Right, exactly. So we didn't have a monochromatic light source, but we kind of got a pseudo monochromatic light source by essentially taking the red, green, and blue components from, you know, any RGB image.
Like transmission filters.
Yes, yeah, and so those are just built into the detector, the sensor, the Bayer filter, I think.
There's RGB filters in the USB camera.
Yeah. So in that case, and I wonder if I have that
Is
question.
it different if you filter before the sample or after the sample?
Is it different?
Yeah.
Before or after the sample?
I would say
I don't
no,
believe
because
so.
these are optically clear, so there's going to be like no absorption.
So the red light will.
No, if there is some cross effect between the other colors.
Oh, I don't think. I'm pretty sure that
Well,
like colors that don't affect
temperature change.
temperature change, maybe. Okay,
some
maybe.
cross effects from the other colors. So
Yeah.
it is better to filter before the sample.
Okay.
If you want to fairly judge, it is better to filter before
Well,
the
I
sample.
do. I have a little like filter right here, so I'll do that when
Yeah, I
do the
know
demo.
that you will filter after the sample.
So in any case, we have, and do I have the equation here? Essentially what we've done is we've said that for anywhere where we have a dark fringe, that's where our phase change is 2 pi, right? Or n2 pi. Strings.
For example, if red will heat the sample a little bit, it will affect the green.
That's true. We didn't consider temperature, though, I think. But you're right. I think like a more serious analysis would probably consider this. So we have a table here of the values that we came up with. We've essentially assumed that this dark fringe. No, I believe we actually said that, and you can't see this because it's too faint on the screen, but we said that the 0th order fringe was at the edge here. which is actually, I think, generally the case. Like when you look at photoelastic objects or any object under stress, there's a concept of like a free edge is like a stressless area. It's not quite the same because these are kind of like these are kind of burnt in stresses, so it's maybe not quite the same, but it appeared to us by kind of studying the colors of these fringes that the 0th order occurred at this edge. And so we measured the orders going in from here. So for each wavelength, we had a value of, we used our stress optic coefficient along with the wavelength to compute the phase change that corresponded to each of these fringe orders. And doing that, knowing our C value, we were able to then determine the stress that corresponded to. And so here's a table of those stresses, and these are divided by the blue, green, and red fringes. So you can see that they're of the order of like kilopascal, which we don't really have a good intuition for pressure really, that kind of unit. But I believe it's the case that an atmospheric pressure, like atmospheric pressure, is on the order of megapascals. So I think kilopascal felt like a reasonable value for the kind of like stresses that are occurring inside this object. We don't expect them to be that large, right? I wouldn't expect them to be that large. So this was our first method. The second method made more use of this chart right here, which is the Michael-Levy interference color chart. And so this is something that's utilized, I believe, quite a bit in like microscopy, and has actually been around for a long time, to my understanding. Like, has been around since the 1800s even, something in this form. And so you can see that these colors that we're seeing here are essentially meant to be correspondent to the colors of these fringes. And it'll tell you, based on the colors that you're seeing in your fringe, where in this fringe order you're actually where these fringes occur, what order they occur in, if that makes sense. And actually, this is the reason we moved to white light, because you can see these fringe colors don't really look a lot like these colors. And this image here was taken with our LED source, like this one right here. And we decided that, okay, probably we're having some weird effects from, you know, the RGB LED kind of white lights that's not truly continuous. And so we're not really seeing these colors that we want to see. So for the next portion, we actually moved, this is where we use the white light. And again, it's maybe not entirely clear, but you can see that the colors, we have a red fringe here in our plate, blue fringe, lighter blue, yellow, purple, and it actually lines up quite nicely to kind of what we're seeing here. So red, blue, light blue, yellow. And again, we took the edge of our plate to be the 0th order, where there's no stress. And moving in from there, I actually put together this kind of like, I tried to essentially like map some like, you know, draw on top of these to kind of isolate the fringes and kind of make them clearer. And then counting these, using a chart just like this to kind of align the color and find what the phase change that corresponds to was. We can see I essentially, okay, this isn't working. Here it is, okay, here it is. So using that chart right here, this chart, I was able to assign values to each of these fringe orders of our shear stress. And you can see they're roughly the same magnitude as the ones we looked at previously, so on the order of 1 kilopascal roughly. So again, we don't really like this. We don't have a good intuition for stresses, right?
How many meters do you have?
Okay, let me move it along. So the point is, we measured the stress of each of these fringes, and we got numbers, which I thought, yeah, kind of interesting. So in conclusion, Luke, do you want to handle the conclusions?
Yeah, sure. So in general, we did 2 experiments. The first was finding the direction of principal stressiness. This was done by determining where the isoclinics occur in the material.
Then from there, we quantified the shear stress planes within two different types of materials and two different methodologies. But in general, we have designed a system that we can use in order to measure the stress orientation of dielectrics. Thank you.
Okay.
And
And
I just want to tell you that in any conference you are allowed 15 minutes.
really?
10 minutes for presentation and 5 minutes for questions. And you should be clever to tell people everything in 10 minutes.
Okay.
But here we are not in a conference, we are in class, but
Mhm.
just as a hint for your future. In any conference, they don't allow you more than 10 minutes. Sorry?
Anyway, it's time for the demonstration.
Okay, let's see something.
Okay, so what I have in here right now is just it's a linear polarizer.
What is at the bottom?
So at the bottom, this is a linear polarizer and a diffusing.
No, what is this light source?
Oh, this is our like light box. It's like a LED light box.
It is like the screen of tablet or something like that.
Yeah, and so
Just connect.
you can see that as I rotate this polarizer, we go from having no light to light. So I think that's kind of like a fun demonstration. It's hard. It's
That's okay.
difficult to see up there, but so let's see maybe some just objects.
Can we see anything with this? Maybe?
Yeah.
Oh,
Okay, that's
yeah,
better.
yeah.
Okay. Maybe I can zoom in a little bit too. Okay, so here's our protractor that you saw in the presentation. And what you'll see as I rotate it, these isoclinics, that dark spot, will kind of move as the predominant direction of stress becomes aligned with the polarizers, right? So as we rotate, the direction of stress will rotate with the object and become aligned with the polarizer.
This is because, as mentioned earlier, these have to be considered as like a collection of crystals themselves. So the predominant stress direction actually changes the function of the angle.
So these triangles are kind of neat. You can see there's like these weird kind of like manufacturing errors that you can kind of see that you don't really see under normal illumination. Like this kind of discontinuity right here, and something, some weird stuff happening up here. Let's see. Oh, I have a red filter here to give a demonstration of some monochromatic fringes. So you can see here's our white light illumination, and you get all the nice colors, which are useful because you can get at a more fine scale of like the order of fringe that you're seeing. But sometimes, you might just want to see monochromatic illumination, which you lose where the 0th order fringe is, but the fringes become much more kind of defined.
Why do you lose where you lose?
Because the 0th order fringe in the white light illumination basically corresponds to where we see black, because the 0th order fringe is where there's no phase change introduced. There's no stress.
Whereas if you only have monochromatic light,
Okay,
you're going to see phase retardation in some type of periodicity.
Can you bend this protractor a little
I
bit?
think that's the thing, is these ones don't bend well. Like if you try and bend it.
Let me
Look,
It doesn't-
stress distribution changes.
Yeah, right. We actually do have a very
I saw a
much-
very nice experiment. People were trying to design a new wing of an airplane, and they made a plastic model. They put it in a wind tunnel, and they blow air at different speeds, and they study stress distribution along this airfoil.
So what we have here is this is just a sheet of polycarbonate, which is the level of stress, or the stress optic coefficient that we use for approximating the stresses. And you can see that the stress in this object is essentially what I would say like uniformly linearly oriented, because we either have it's entirely isochromat
Can you try
or entirely
some
one
shear?
isoclinic. Yeah. So as you bend it,
Yes.
you start to get the colors, and if you kind of bend it a lot, you start to see all the different fringe colors show up. So it's pretty neat. We did take
But
some.
quantitative analysis is preferred with monochromatic lights. So you study quantitative analysis with different colors. Because with white light you just see nice shapes, but you cannot measure a lot of data.
Ooh, yeah. Does anyone have anything they want to put in here? Anything clear that they'd like to stick under here?
No, just stress it.
Stress. Okay, this one's neat. This is like this looks like a radial kind of thing too. Oh,
Look, if I pull it, if I bend it, if there is a shear,
Just
yeah.
break it.
Look at that. Just break it. Actually, breaking it didn't really seem to like make any sort of really like interesting stress inside of it. Strange. We tried that.
Something that we can
Like
Yeah.
when you break it and
Like when you break it, it didn't really like lead to any built-in
stress
stresses.
increase till threshold at a point, then crack growth starts from this point.
That part has a fracture on it.
Oh no, so that's interesting. Like if I actually remove this, if I remove the polarizer here, you can see that there's like no real sign that that is even in there. There's no, but then you put this in and you can see
Everything
that there's
because of polarization.
very clearly this like weird manufacturing defect or something.
These are called crossed polarizer analyzer set.
Well, anyways,
Yeah, so.
thank you everyone.
Oh wait, maybe one more thing.
If you rotate this 90, if you rotate 90 degree, you will not see. You must start with crossed.
Yep. All right.
May I check my glasses?
Yeah, do it. So yours might actually be glass. Mine are plastic, so you get those.
No, mine is plastic,
It is.
but it is
Must be much better plastic than mine.
yeah, it is progressive.
Where's mine?
So stress distribution is nearly nothing.
oh, nice.
So it is not. It is well heat treated after production.
Expensive.
Yeah.
Not expensive. Do you know what is meant by heat treatment? After production of any mechanical part, there are a lot of internal stresses embedded during machining. There is some heat treatment to release all internal stresses. Right?
Well. All right, so
Okay. Do you like the experiment?
Yes.
Okay. So you got a C.
See?
Because they like it. Thank you so much. The next group, please.
Here you can move this back over.
Heat treatment is a very, very essential step in any production.
Oh yeah, that's
Like any material.
Any material, because during machining you apply a lot of stresses to cut, to shape, to after that your material may be very fragile. When you start to use it, it will break quickly. So heat treatment means to release molecules, make them more elastic again, more strong again, right? For every type of material, there is a very precise steps